All right, good afternoon. Welcome to the last seminar of winter term, and I wish everyone a good finals week next week and a good break. My name is Robert Bertini, and I'm one of the organizers of this seminar series, along with Jennifer Dill and Chris Monsieur and John Glebe. And today, it's my pleasure to be the lead-off speaker. We'll be talking today about a project called Portal. And Portal is the Portland, Oregon Regional Transportation Archive listing. And we're going to discuss lessons from developing our archive data user service in Portland, Oregon. And I'm hoping to minimize my role as speaker, but unfortunately you're stuck with me for the introduction. And then I'll be introducing part of our team who are collected here in the front of the room. And each team member will have a role in the presentation as we proceed. So we've been doing this seminar series for, I guess, about 6 years now, and I noticed that we had a student present a seminar about Portal back in 2005, but some of you may not have been here then, and so we thought it was high time to update you on the work that we've been doing here on the Portal project. So we'll talk a little bit about, I'll give you a brief introduction and quickly show you what Portal is. We have some team members who will be talking about some various new components of Portal. And then at the end, if there's time, we've recently conducted a user survey, and we have some results from that and some success stories to share with you about the project. What is in our database? It's a transportation archive listing. Since 2004, so 975 days ago, I believe, we started archiving data from about 500 freeway sensors in the Portland metropolitan area. I think the database is about 300 gigabytes now, and I just tallied this up that there were about 1.2 minutes in those 975 days, and we get a reading 3 times per minute from the 500 sensors on the freeway. So on the upper left here you see every 20 seconds we receive information about count, occupancy, and speed from the freeway detectors, and the average spacing of those detectors is a little bit over a mile here in Portland. We also have in our database incident data from 140,000 incidents, and we have weather data, which we won't be talking about too much today. And we also have recently added variable message sign data from the 19 variable message signs here in the Portland area since 1999. And there are even more VMS around the state. And so we're talking with ODOT about tools that we can develop to help them understand how those VMS are being used. So that's what's in there, and you'll be hearing more about what all this means. What's behind the scenes? I like to, these are fun things for us here at the university with this large database. So we have a database server. We have a development server that the team members work with. We have an open source, if Microsoft is listening, we have an open source philosophy and just reality in terms of the budgets that are available. Some archive data systems around the country use Oracle, but there are large license fees associated with that, so we prefer the open source feel. We have a large storage device that was actually paid for by the Federal Highway Administration, 2 terabytes in a disk array, and that's infinitely expandable. When I first came to Portland State, people knew me around the campus for wanting lots of storage space, whether it was for my website or my desktop computer. But when you work with data, you need lots of space. And fortunately, in the last 7 years since I've been here, the cost of that kind of storage has come down a lot. And so people say, well, how long are you going to keep this data? We started in 2004. And I said forever as far as I'm concerned. So we really have to adopt this mentality that we want to archive all of our transportation data because you never know how we might want to use it in the future. Then finally, we talk to the world using a web interface. And what I thought I would do is I've been having trouble with this, but I'll try to leave PowerPoint for a second and go to the web interface. So thinking about the freeways in Portland, does anyone have a favorite freeway? How about northbound I-5? All right. I was hoping you'd say that. So this is within our website. We're looking at today, March 16th, I-5 north. I've asked Portal to plot speed. So right here, thanks to Kristen Tufte, who's our one of our team members, this is a time series. So this is midnight this morning, and this is just noon, just about now. This is Wilsonville down here, and this is the Columbia River on northbound I-5. So this shows the actual measured speed along the I-5 corridor from this morning. And some of you may have been on this freeway during this time. And so what's this little red area where the speed dropped down in Terwilliger Curves? Okay. When I ask this question in China or Japan, people don't know about the Terwilliger Curves. But here in Portland, it's an easy answer. So this is just one little sample. You can look at what's happened. You can look at several different performance measures. But basically, we can see how the system is performing. And that can be very useful to us, not only in real time, but in thinking about what we want to do with our transportation system in the future. It's kind of nice to know how it was performing today or yesterday or last year or even the year before. So I'm going to go back to PowerPoint, I hope. And so just a few more facts. I've already described kind of conceptually the database. This map shows actually the freeway network and the closed-circuit TV camera locations. There is quite an extensive intelligent transportation systems infrastructure in the Portland region with about 100 cameras, 138 ramp meters. TriMet has an extensive automatic vehicle location and bus dispatch system. All of these devices are connected essentially with a fiber optics network, and Portland State is on this ITS network. It's a private, high-speed transportation data transmission network, and this is essentially how we receive the data in real time. We also think of ourselves as a bi-state region, so Southwest Washington is part of our regional concept. We're working with the RTC in Vancouver and the city and WashDOT, and we are set up to receive WashDOT freeway data, and I'm told that any minute now that will start flowing over our network. So perhaps the next time we talk to you, we can show you some results from Southwest Washington. There is a strong regional commitment in the ITS community here. Basically, that's what makes this possible. This project wouldn't be possible if the transportation agencies weren't partnering with us and providing the data to us. So the data sharing philosophy, I guess I tend to think that should be the philosophy everywhere, but that's kind of a unique philosophy here in Oregon where people are anxious and willing to share data. And Portland State is the official data archive entity for the Portland metropolitan region. So within Portal, we have, I mentioned that the detectors that are on the freeway are recording count, speed, and occupancy, and those are the fundamental measurements that we receive. We convert those to 4 other measures: vehicle miles traveled, vehicle hours traveled, travel time, and delay, and we'll be showing you some examples of how we use those. But these are our 7 fundamental performance measures. There are a few other performance measures in transportation, but most of them, if you boil them down, come down to these basic values. I showed you the home page already, so I'm sure some of you right after this seminar are going to go out and request an account with Portal. You can all join as users. But this is how we talk to the world, and we have a little list of kind of administrative things here, and then we have a list of what we call tabs that users can interact with, and I'll give you some examples of how those tabs work. I've showed you the time series, which allows you to look over time and space at a particular performance measure, but there are some other tools that we have as well. This is the time series speed that I've shown you already in real time. You can pick a corridor and a direction. You can pick a date. You can pick one of those 7 performance measures. You can choose whether you want to look at a particular lane or all lanes averaged together, and you can pick a time period. the version I showed you was for all of today, for the whole I-5 speed averaged across all lanes. So this is also for I-5 North. It is my favorite corridor to show because it's an interesting, it shows some dynamics over the day, right? You have the morning peak coming northbound, Terwilliger curves, and then you have the afternoon peak going back into Vancouver. And I think Catherine is one of the people in that northbound, this right here. So you look at a plot of speed, for example, and you say, well, it occasionally rains here in Portland, so could the weather have had an effect on the congestion pattern that you observe? Fortunately, we thought of that, and you can click on this little button that says Weather Pop-Up, and you can look at, for that particular day, a time series of the temperature, which is the red line, and then a bar chart for precipitation. So if you go into Portal and you try to use it, sometimes the weather data takes a couple days to get into the system. So if you try to look at yesterday, the data might not be there yet, but usually within about 3 days we get the weather data. But that's kind of useful if you're trying to, as an analyst, trying to figure out what's happening on the system. Also, as any of you who have worked with real data know, real data is interesting because it's real and it has holes in it, and there are gaps and physical devices out there that get wet or break. Communications networks come and go. Power comes and goes. So data quality is a big component of our work. And you can also look at a data quality plot that tries to give you a picture on a scale of 0 to 1 of the quality of data by time and by location of the sensor. We also have a tool that allows you to look at, well, there are different types of data failures. There's suspicious data, there are communications failure, there is good data, and then there are periods of time when there's just no traffic being measured, which is, on one hand, okay, because usually in the middle of the night, a 5-minute period could go by and you don't see any vehicles. So we try to give the user tools to make sure that they have a picture of the quality of the data that they're working with. In addition to corridors, you can also choose to look at data from a particular point. So this box here, you can pull down and choose a particular detector location. This happens to be Delta Park, northbound I-5. This is volume, so you can see for a whole day what's going on with the volume. Goes up, right? Then it drops a little in the middle of the day, and then there's a peak, an even higher peak in the afternoon before it drops off again. So we call this the peaking phenomenon in transportation, that most aspects of transportation have peaks in them, and that's why we have jobs, because we have to help deal with the peak periods. The off-peak period over here between midnight and 4 in the morning, usually that's not where we focus our attention. Now that was just one snapshot of volume data for one particular day. We've got almost 1,000 days of data now, so we can start doing some things where we take advantage of the fact that we've got data from multiple days. And we can look at the concept of reliability. So this is also for Delta Park, and it shows its travel time over the Delta Park segment of northbound I-5. And what this shows is travel time just on weekdays for August and September 2005 for the whole day. And what we're showing is the mean plus or minus 1 standard deviation. So for that 2-month period, we have the mean value as these little dark dots, and then plus or minus 1 standard deviation. So what can you see that's happening, or can you see what's happening later in the day? There are 2 things that are happening.
Higher volume and more variation.
Did you use your microphone? Exactly. So the volume, the mean value of the travel time goes up actually quite a bit in the afternoon, but also the variability goes from almost 0 to quite a bit. So from day to day, you're seeing quite a bit of difference in the travel time that's being experienced. So Some people argue that, of course, travel time is important, but the variability, so the unexpected, really long travel time can, for a person or someone trying to ship some goods, could be even worse than the fact that the travel time has gone up. So this right here saves you about 2 weeks of lecture in a fundamental traffic flow theory class, because you can just look at the data and learn that as we just heard. So this is a little extension of that reliability concept, and this is for the whole northbound I-5 corridor. And Mark Hallenbeck at the University of Washington started producing these kinds of plots for the Seattle area freeways. And we've got these automated within Portal, where you can pick a month and a corridor. Again, I-5 North, my favorite. This green line here shows the average travel time. So again, you can see the two peaks for northbound I-5. This is about a 23-mile corridor. The red is the 95th percentile travel time for that particular month. So you can see that the gap between the 95th percentile and the mean, say that you are either you have to be on time to your job or to pick up your child from daycare, or say you're shipping something to somewhere and you have to be on time with the delivery of that item. And if you need to be on time, let's say 95% of the time, just because we've got that plotted here, and you need to travel at 8 o'clock in the morning, this shows that for that northbound corridor, you'd need to allow about 52, 53 minutes of travel time, whereas the average was more like 32 or 33 minutes. So 20 minutes of buffer time just to account for the fact that something might happen to delay you is quite a valuable piece of information to have. So you can plan your trip knowing that a little bit more intelligently than otherwise. And so these monthly plots are you can produce automatically within Portal for any month, for any corridor. And then what I didn't mention is that the blue bars in the background show the percentage of the time throughout the month that corridor was congested. It also, the last thing that it reveals is during the middle of the day, let's say from 10 to 1 o'clock or so, that red curve just about touches the green curve. So this is a little different than other metropolitan areas where that peak or that low reliability exists throughout much of the day. So this is something for those people who want to be pessimistic. I would say, well, we've still got some capacity during the middle of the day here. We also produce similar to the last one, a monthly congestion report. We also, many of the elements that I've already mentioned are available in a daily dashboard, and we originally prepared this for Matt Garrett, who was the Region 1 ODOT manager. He's now the director of ODOT, and he was visiting us, and we prepared this dashboard for him to be able to go in and see, well, how's my system performing today? How does it compare to how the system performed yesterday? We're not sure that he ever actually did that, other than the time that he visited us, but one of our missions is to produce tools that others can use, and so this was an example of a tool that puts it all there right in front of you. Something else we've added, I mentioned the incident data. There are about 20,000 reported incidents on the freeway network here in Portland every year. And where do those incident data come from? Well, ODOT has a traffic management center just a few blocks from here, down on Flanders, and they have staff in there who essentially enter data in their database. There are 92 fields, so each incident basically has 92 categories that can describe it. On average, as incidents evolve over their life, because there is an evolution, the incident occurs, it gets reported, it's verified, there's a response, hopefully it's cleared, and then at some later time the traffic clears. So there are often updates that are in the database. There's an average of 4 entries per incident. Clearly some incidents there's just something out there and then it goes away, but other incidents last much longer. So this is an example on the time series tab. you can select this incident box, and then when you plot the time series, this is speed, for example, it will show you actually the location, the start time, and the end time with this little bar of a particular incident. And this was one on northbound I-205 back on November 15th, 2005. It was an incident that was quite substantial, as you can see, this congestion that resulted from it. It was, and when we dug into the database, it was actually a big mess. A log truck rear-ended a nursery truck. It was an over 4-hour incident. And on our incident tab, we select some of the fields that you can actually see at the bottom for each incident, even if we don't know the location exactly. If we know the highway, we tabulate all that information. What I'm not showing here, but if you plotted the speed for the same day for southbound 205, you could actually, well, no, I guess there was an incident southbound 205, and this little yellow strip is due to the rubbernecking for that incident. If we showed the southbound, you would also see the rubbernecking for this particular one. So we produce monthly incident reports, again, aimed at the ODOT managers who handle the Comet Incident Response Program. So we produce these pie charts of the types of incidents, the number of lanes they affect, the locations of the incidents, and then the bar or the line chart on the lower right for the whole month shows the average number of incidents active at any moment in time. And it's a little hard to see, but this is 4 right across here. And so at the most, there were about 4 active incidents during this particular month. And so ODOT can use this to say, well, how many incident response vehicles do we have out there? Most of the time in the peak, they have about 4 who are patrolling the freeway system. So at some point, if this goes up to about 5, they would want to say, well, okay, we need to reshuffle our staffing and perhaps assign another vehicle to the incident response. So within Portal, we also have a mapping component. This is just an example. You can pick a time period. You could look at a snapshot right now and see what the conditions are using our map. You can also look at average conditions over a whole month. This just shows July 05 and December 05 between 5 and 6 p.m. You can, to highlight the difference between 2 time periods, you can subtract one map from the other. And so this shows the difference between those 2 maps highlighted. So the red areas, you can see there was a fairly large difference in speed. So this could be useful to observe how conditions are changing over time during particular peak periods. In traffic, we like to plot data in certain ways. So this tab allows you to plot 2 of those variables that we measure against one another. This is a bivariate plot of flow versus occupancy. And you have to come and take one of my classes and then I'll tell you what this one's about. We'll talk a little more in a few minutes about data quality, but we're trying to help ODOT increase the quality of their data, and so we can pretty simply provide them with a list of detectors that are producing bad data. They can go out in the field and focus their attention on repairing those detectors, kind of like David Letterman's top 10, the top 10 problem detectors. So this way, it's not a mystery. They can focus the resources in the areas where they need to focus them. Then I'm going to turn it over to some of the students here in a minute, but I also wanted to mention that we've expanded our system a little bit to include an area called Google Traffic, and we presented a paper at TRB this year that describes how this works if anyone's interested. But basically, this allows you to upload and manage traffic data files. So in the traffic engineering business, a lot of time and energy and resources are spent essentially counting traffic. And I know when we have a project that involves traffic counts, the students think this is just fascinating, and they're really excited to go out in the field and stand in a corner and count cars. And it's fundamental to what we do. But this is a tool that allows users to upload intersection counts or traffic counts of any kind and associate them with a particular location. So that, say, for example, you had a traffic study at a particular corner, you could go into Google Traffic and see, well, has anybody else done traffic counts there before? That could help inform your study, perhaps help save you some time and money in going out and doing new counts. So that's kind of a snapshot of where we are with Portal. We have a lot of data. We have a lot of tools that are available. Some of the directions that we're heading involve adding new data sources. So we've done a lot with the freeway data. We're adding the state of Washington's freeway data in the near future. We've got essentially a new thrust looking at transit and arterial performance. So we have 2 graduate students and 1 undergrad who are going to talk about their work on this part of the project. And first, we're going to have Matt Burko, who's a MERP student, and I'm going to turn it over to Matt.
Okay, thanks, Dr. Bertini. So I'm a first-year Master of Urban and Regional Planning student at PSU, and Michael and myself are we're going to be working on studying Barber Boulevard, basically combining data that we can get from buses, transit data, and Michael's been looking at loop detector data. So up to now, we've been really individually looking at I've been looking at the bus data, he's been looking at the loop detector data, and in the end, we're able to marry these 2 data sources together to ultimately present a more complete picture of what's going on our arterials, on the roadways, and ultimately hoping to, okay, how do I turn it on? Says it's on. Yeah. So, I guess my parents watching won't be able to hear what I'm saying. No, they're not really watching. So, and ultimately hoping at the end to generate a map, kind of like the ones we were seeing with Porto, that could show the arterials in different colors representing
How do we do that?
Okay, so this is an example of the data that I've been getting from TriMet. So just to give you an idea of some of the fields that I have, I have the date of service, I have the route number. Also, we have the time that a bus arrives at a given stop, the time that a bus leaves a given stop, so it's the arrival and leave time, and also the stop time, which is the time the bus was scheduled to make that stop, so we can tell if it's running late or early. And we also, buses have units that count passenger.
I think there's a problem with the noise. Sorry for that.
No problem. Sorry, give us a try. Okay. Okay, so so generally the bus will record a row every time the bus either stops and opens its doors or it passes a scheduled stop, whether or not it stops at it at all. So in addition to information, the bus is recording people who are getting on and off the bus. And there's a record when the door is opened, and there's how many people got on, how many people got off, and the dwell time is the amount of time in seconds that the door was open. And one of the challenges with the bus data, if it's going to kind of approximate for us levels of congestion and whatnot, we need to separate out the ways in which a bus is not the same as a car. So being able to separate out this passenger movement and this dwell time helps us to understand if a bus's delay is not a result of congestion, it might be just a result of a lot of passengers. So this is just an example of when I first started to look at this data. So this one is just the total travel time for the bus across time. So each dot represents one trip, one bus run. And it's just kind of showing that buses are subject to congestion. You can see that during the peak periods it takes much longer than the bus to do the same route later on in the day. And the lower right slide shows total trip time versus the mean speed. So one other piece of information that the buses record is a maximum speed value. So if you have 2 stops, it's hard with the microphone, but if you have a stop here and a stop here, when it gets to the second stop, the bus records the maximum speed that it attained between those 2 stops. And so again, if there's congestion, you can suspect that the bus will probably reach a lower speed. So I plotted the average of all those max speeds for each route or each run versus the total trip time. So again, you can see that the average speed does reflect how the total time that the bus is taking. Okay, and this is Another way of looking at the data, so this is, again, time across the bottom and distance, and this is giving each color is those max speed values. So this is just a quick way to look at a lot of data. This is the bus 72, which runs along 82nd Avenue, for 1 day, which is about 12,000 rows of data. And so what you can kind of see, the red is the slower speeds, and you can see that in the early, around 7 a.m., there's some slowness, also kind of in the middle of the day, and then another there kind of in the afternoon peak, 4 to 5 o'clock. So this is just another way we can view this data. And I think I'm going to skip a couple of these slides, although this is just a list of the different ways we can look at that dwell time, the time that the bus is serving passengers. And this is something that we can calculate really quickly. Okay, so I was going to, one of the important measures for transit is headway. And I'm going to use headway to kind of give an example of how this data can be used to kind of tell a story about what's happening on the roadway. So headway refers to the spacing between buses. So for example, TriMet offers 15-minute service often for its more busy routes. And so this is important for passengers because passengers are responsive to the amount of time that they're waiting for a bus. So they want to know there's a bus coming regularly. So the question is, what happens if a bus starts getting late? So if you have 3 buses, that should be 15 minutes spaced, and one of them starts to get late. It's starting to get close together. So it's now the spacing between the 2 buses is, say, over 20 minutes. Let's say the bus is running 7 minutes late. So now what happens is when that bus shows up 7 minutes later at a given stop, there's going to be more passengers there. And when the passengers are getting on the bus, they have to feed their money in the machine. And so this is going to further compound that delay. And so the bus, that delay tends to, like I said, compound on itself. And so this kind of gives an example of this bus, which started about 7:27. At the beginning, they were roughly 15 minutes spaced, but the bus starts getting delayed. And the red on this map shows times when it stopped to pick up passengers. So you can see it's picking up a lot of passengers. So probably it may have initially been delayed because of congestion. It's kind of difficult to say, but it is picking up a lot of passengers. And what happens as the second bus, meanwhile, comes to that same stop maybe 5 minutes later, now there's not very many passengers there. So that bus is progressively catching the other bus. And this is what you see. You can see the 2 buses ultimately get really close together. And as they get close together, that second bus is not picking anybody up. So this is useful for just kind of understanding what was happening out there on the roads. So the idea is that hopefully we can use the bus data and the story that it tells just to complement the loop detectors, because loop detectors and arterials may be spaced over several miles, whereas we have literally thousands of records of bus data. So together we might be able to have a more accurate picture of what's going on. With that, I'm going to turn it over to Michael. Okay. Oh.
Skipping a couple more slides now?
Yeah. Okay.
Okay.
Let me give this to you.
All right, so as Matthew says, the buses generate a lot of data for a particular trajectory over time, whereas I can give you a lot of data for a particular location in space. And so the ultimate idea for combining our two projects is to sort of set up this matrix wherein we can say a lot about particular points over a long period of time, or a lot about a particular trajectory over a long period of space, the whole corridor. So this was the corridor that I studied. It was Barber Boulevard. And the sort of the impetus for using this stretch of road was that we have a good install base of loop detectors here, so there's the data available. I should back up a moment and say that the goal of my project to do was to study arterial performance. Well, there are a number of ways that we can talk about arterial performance. Dr. Bertini mentioned several ways that we talk about performance of freeways, and those are all germane here, germane to arterials, but also you can add things like signal delay, signal coordination, and various other measures. So, it's a good idea to keep in mind just what you're measuring when you talk about arterial performance. And then, as Matthew pointed out, there are a number of different ways to get your data that tells you how your arterial is performing. And what I was doing was looking at loop detectors. And so you can see Barber Boulevard as it goes from roughly I guess, the Capitol Hill area all the way to the edge of downtown. And I've created this sort of linear schematization of the road over on the right, and it tells you the relative locations of the loop detectors that I got my data from. And so, so the idea was to take the data from the loop detectors and turn this into, oh, doggone it. Okay, into this. So just as we see in Portal, we have a color-coded map that gives travelers an indication of just what the current conditions are on the arterial. And so you can see the colors on the map and then translated to the schematic diagram. And that sort of gives you an interesting tie between this color-coded map and the pseudocolor plots that Dr. Bertini was showing earlier in the presentation. So what the pseudocolor plots are, they're just the schematic run shown as it changes over time, set all next to each other. And so the first thing that I did in looking at this data was I made some charts. So these are pseudocolor plots that show just the varying levels of occupancy during the day at the loop detectors that I had data for. And the whole goal of this was just to get a feeling for the data, just to see where the peaks and the valleys are, and to see if I believed it, right? To see if it gave me a picture of Barbara Boulevard that was believable. And I think it really does. So this is northbound on Barbara Boulevard from Capitol Hill towards downtown, and you can see that there is a major peak area in the morning as you get closer to downtown, and so much so that you get some very heavy congestion as you get to the very edge there. And so I thought, okay, well, this is very believable. In order to actually generate a performance map, you wouldn't want to do this necessarily. It would be necessary to go out and actually set your thresholds between the colors at a point that indicated a distinct difference to the traveler on the arterial. You wouldn't want to say, well, this is red and this is yellow arbitrarily. You would want that difference to mean something to the traveler, like saying, oh, it will take me two cycles of the signal to get through this intersection rather than just one, for instance. Okay, so what I've done here is I've focused on the morning peak area, since that's the most interesting part of it, and I've plotted over that sort of virtual vehicle trajectories. Another piece of information that I had in addition to occupancy was average speed for a 5-minute period. And so all I've done is I've said, well, okay, if a vehicle is in fact traveling at 5 minutes, at this average speed in this period of time in this location, well, then how long will it take it for it to traverse to the next detector, right? And so these don't represent the actual paths of actual vehicles on it, but rather it gives you an indication of just what kind of conditions a vehicle at a point in time, at a point in space on Barber would see. And you can sort of string them together to say, well, it's traveling at about this speed between the Park and Ride and Bertha, and then across Bertha it's traveling at roughly this speed. And so you can sort of get an idea of just about how much time it would take to travel the whole distance. But because it's subject to these sort of local transient phenomena, you get wacky things like a car starting back here taking longer to travel between the Park and Ride and Bertha than one that starts 5 minutes later. And so clearly that's, you can't take it literally, I guess. So what I've got here, this is just looking southbound out of downtown. I'm not going to focus on this too much because it doesn't really provide too much more illumination. And this is with the southbound peak with, again, the average speeds sort of projected on top of the plot. So what I've done here is, this is kind of a bit of spaghetti, but what I've done is I've gone back to the northbound into downtown peak hour, and I've added trajectories of the buses because I have bus data on top of that. And it's pretty interesting. It's a bit much to process at once, but you can sort of see that there's some conflicts up here between my sort of assumed vehicle average speed trajectories and the actual trajectories of the actual buses. And so I have the next slide takes the virtual vehicle trajectories out to clean it up a little bit. And here it becomes clear that that the bus trajectories don't line up quite perfectly with the areas of congestion. And I think part of that was because the assumption that I made when I made the original pseudocolor plot was that the conditions monitored at a detector applied to that point and the entire length of roadway until the next detector. And so I'm making assumptions about areas of road that are about as far from the detector as I can get. And so I thought I could start to bring Matthew and I's projects together by using his bus data to maybe see if I could make a better assumption about what my detectors told me about the roadway. So what I did was I instead decided to say that the detectors told me about the area of roadway between halfway to the previous detector all the way until halfway to the next detector, and see if that maybe gives me a more realistic picture. And so I did that. And it's just the same data for the same period of time, but with that updated assumption, I get something that looks a little bit more realistic. I've got the buses slowing down in the middle of the congestion area rather than at the edge of it, and it's on the whole a bit more satisfying. And so that's sort of the way that Matthew and I have been working together to say more about arterial performance.
Very much, Michael. Next, we have John Chi, who's an undergraduate in computer science, and he'll be showing you how he's been automating what Michael and Matthew have been working on.
Yeah, so we also developed a policy for tossing out, well, not tossing out records, but flagging records based on certain air conditions. Like, we found that the buses had records where a bus arrived at a stop before it left the last stop, and we said, that doesn't work. We don't want to use that data in our applications. So we flag it, and by flagging it that way, researchers are able to look at the data and develop like data fidelity information based on the data that we got from TriMet and that was aggregated. The database representation of this data, we have two tables, one for the raw, direct from TriMet CSV files, and one for the aggregated data with the data quality flags. They can be accessed internally by users or applications, just with direct SQL queries. Researchers can use it internally and export to CSV or other popular formats. However, they need to use it, Excel or MATLAB or whatever's convenient. And having all the data in one central location really speeds up application development. We don't have to, handle these, zipped huge CSV files and pass them around to all the application developers. We can just have one central place where we pull the data from. So this is a Google Map interface that I've worked on, and you can see that you can choose the map plot type here. This is showing the lines, and the lines are color coded by maximum speed. You can pick a route. I've chosen route 15. You can choose a corresponding date. This is September 17th, 2006. You can choose a trip that corresponds to that route and that date. And you can choose a speed range, 0 to 40 miles per hour. Down here it shows you a short summary of what your query is processing. You can see the number of stops in this range and the average speed. And here is the actual cool stuff, the drawing of what's supposed to be happening on the roads at that time. This is the same plot, or same information plotted with markers instead, and you can see that you get some more detailed information, such as the stop location, the maximum speed, the load, and train mileage. We have some planned work. We'd like to implement graphs directly into the portal web interface so that researchers who don't have direct access to the database can create graphs such as bus trajectories, on-time performance, headway variance, the kind of things that Matt and Michael have been working with. The final goal, or the primary goal for the Google Maps interface is to emulate the ODOT speed map for arterials. It'd be nice to be able to look at Portland and just see, like everywhere TriMet travels, we've got speeds for that area. That'd be cool. You can check it out at our test area under the TriMet analysis tab. Thanks.
Thanks, John. Let's give John a hand. And next is Kristen. Thank you. So Kristen Tufte is a postdoctoral research associate in computer science and civil and environmental engineering, and she's been working on the portal project for almost 3 years now, and has been overseeing John's work as well as other students' work. So Kristen's going to talk about a project that we've been working on with ODOT to improve the travel time algorithms for the freeway system, and then also, I mentioned earlier, the variable message sign data incorporated into the system.
Okay, thank you very much. My name is Kristen Tufte, and I'm research faculty here at Portland State University. I work both in computer science and in civil engineering. And I'm going to talk today about both the travel time project that I've worked on and a project involving incorporating the variable message sign data into the portal database system. So first, travel time project. This is a project that I've worked on with Sarisha Koturi, who is unable to present today, but this project wouldn't have happened without all of her help, so I appreciate that. So what is the goal of this project? So the goal of this project is to try and understand the accuracy of algorithms that are used for travel time estimation. So why do we want to do travel time estimation? So ODOT has a lot of these signs, the variable message signs that appear around the Portland area, and they would like to put information about travel times on those signs to help drivers make decisions about, just to provide information to drivers about expected travel times along certain lengths, as well as to allow drivers to make decisions about route choices. So, but before we put the travel times on those signs, we'd like to make sure that the travel time estimates are actually accurate. So what is the methodology of the study? So what we're going to do, what we are in the process of doing is we have a little PDA devices. They're little Garmin IQs, and they collect information about location. And so we can actually send people out to drive around the highways, and they can drive the highways during the peak periods, and they can understand we can get from that data collection actual travel times. So we go out and collect actual travel times using these GPS units, and then what we do to understand is we take the data out of the Portal Data Archive. And using the data in the Portal Data Archive, we estimate what we think the travel times during those peak periods were. And then we compare the actual travel times to our estimated travel times. And this allows us to determine how accurate our estimates are. So this is really an example of how we use the data in the Portal database. We use the Portal database to estimate the travel times and evaluate that accuracy. What I'm going to talk about today is data on I-5, and I don't think I have I-205. We have 48 runs analyzed so far, and we're in the process of collecting more data, and so we'll have more data analysis in a couple months. So the basic problem here is to take this inductive loop detector data that we have from the freeways in the Portland area and to use that inductive loop detector data to estimate travel time. And so why is this not always right, and how can things go wrong? So one thing is, if you imagine a driver driving down a highway and he gets to a variable message sign, and that variable message sign is going to say, okay, it's going to take you 10 to 12 minutes to get to downtown from where you are. Well, now, we need to present that travel time to that driver at the time the driver gets to the variable message sign. So the estimate may be wrong because simply the conditions may change as the driver gets closer to downtown. So we are having to use sort of prior data to estimate what's going to happen in the future, and that's one source of error in travel time estimation. Another source of error is that the data that we're using to estimate these travel times is point data. So it's data from inductive loop detectors along the highway. And in Portland, there are detectors at each on-ramp into the highway system. And the on-ramps may be half a mile apart. They may be a mile apart. They may be 2 miles apart. So we're using speed at a particular point in space to estimate speed over a long, a mile segment. And that, we all know that there is error in that. So there's two types of errors. And one part of this project that we've been trying to understand is, where are the errors coming from? Is it conditions changing over time? If it's conditions changing over time, then maybe we got to go back and look at historical data, and that will help us. If the problem is conditions are changing over space, then maybe the best thing we can do is go add some new detectors, or can we somehow algorithmically accommodate for either error? And how am I? Can't see the clock. Okay, so this is initial set of data for northbound I-5. These are not all the runs. These are selected runs, and in particular, I have left out, I believe, a lot of the uncongested runs. Let's see, can I just check? I need to look at the clock. Okay, so what you see here in the first column, there's a run ID, there's a start time, so this is the start of the, when the vehicle began traveling along the segment. Let me say, this is a segment from the VMS down by Carmen Road, so sort of I-5 south of town, from the Carmen Road VMS to downtown Portland. So this is the time at which a vehicle actually arrived at the Carmen VMS. There's a probe travel time in seconds. The next column is our estimated travel time. There's an average speed, our percentage error, and then we've classified these runs as congested or not. In some cases, as in run 3, you'll notice that we have severe congestion and a 15% error. You'll also notice that in some cases, as in run 1, we have high congestion but a low percentage error. So let's just take a look at a couple of these runs and see if we can see what's happening. This is a graph of the runs for run 3. This is a run where we had a high amount of error. So what you see in this graph across the horizontal axis is the milepost. So 290 is approximately the milepost of the VMS, and you continue on to where 300 is about you're at downtown. The vertical axis is speed. And these blue dots represent the speed that the blue dots represent detectors. And the speed, that's the speed that the detector reported at the time that the vehicle got to the variable message sign. So these were the speeds that were used in the travel time estimation. So in this area, you can see that the speeds are, let's see, the purple dots are the speeds recorded by the probe vehicle as it drove through this segment. So you can see up in this area where the speeds sort of match, the speeds of the probe sort of match the detector speeds. So there we probably get a fairly good travel time estimate. If you look at this section, you can see here that the speeds reported by the detectors are significantly higher than the speeds that the probe vehicle was experiencing at that time. And so this right here is really where the travel time error comes in, the travel time estimation error comes in into this probe run. And if actually there's other sorts of data that we can sort of look at it. And what actually happened here is that the congestion at this milepost increased after the vehicle passed the variable message line. This is a similar graph for another run. And this is a case of congestion clearing. So again, here we can see the probe speeds are much higher than the detector speeds reported for those mileposts. Okay, so this is the travel time project. So again, we're looking at the accuracy of travel time. One thing I want to say is that we think estimating the travel time accurately is important, but actually it's possibly more important to understand the reliability of the travel time. For freight companies, reliability is much more, is probably more important than the actual travel time itself. And another thing we really want to try and understand is how do we tell, just looking at data, when are estimates accurate? We really want to know, do we have an accurate enough estimate to give to the general public? Or should we just say, oh, travel time is greater than 20 minutes and that's the best we can do at this point? So we'd like to understand when our estimates are accurate. Okay, I'll just quickly talk about variable message sign data. So like Dr. Bertini said, we're trying to expand the types of data in Portal. And one way we are working on that is the variable message sign data. So variable message signs are these things shown in the picture right here. You might know them as amber alert signs. They show travel time. They show information about accidents. We currently have at least a year of variable message sign data provided by Oregon Department of Transportation, working on incorporating that into Portal. This is just a quick picture to show you what the raw data looks like as we get it from ODOT. And then we convert it into a table in the database. You can see what type of information we have. We have a timestamp, an operator ID, and the text of the message. The goal is to eventually display the data in Portal, sort of similar to how we display incident data now. So previously, Dr. Bertini showed you this time series plot, which shows time on the bottom and milepost on the vertical axis. And so what this is showing you is that there's a variable message sign at milepost 298 on Highway I-5, and that starting at approximately 3:40 here, it displayed a travel time of 10 to 12 minutes. And then I can't quite see the number here, but approximately 4:20, the travel time message switched to showing a travel time of 12 to 15 minutes. So what we're trying to do here is to correlate the message that was displayed and what the people that saw that message experienced. So if the color of the message sort of correlates with the background color, we expect that probably that was a good travel time estimate. If, for example, we saw 10 to 12 minutes on a red background, we would be concerned that the travel time estimation was wrong. This is some work that was done by, these plots were actually done by an undergraduate, Max Stevens, and another graduate student in the Portal project, Priya, is working on incorporating these graphs into the actual Portal system. And now I'm going to turn it back over to...
Great.
There you go.
So let's thank our team members. Thank you, Kristen. So I think I'll talk for a couple minutes about our recent user survey. And we have about 200 users registered, and we got 40 responses. And we're trying to find out, because this is a research project, sometimes people are using it as if it's a real, reliable, funded sort of thing, but it is a research project. So we wanted to find out for our research purposes who's using it and how they're using it and how it could be better. So this is just a breakdown of the types of users. About a third of the users are either students or faculty from around the world. Actually, we've got users in many other countries who are using the data for research purposes. Although about half of the respondents are in the planning, operations, and engineering areas, and I think many of them are here in the Portland metropolitan region. Types of employers, again, that one-third university, pretty big chunk of private and consulting firm users. I know that local consulting firms are using the data for projects that they're working on for ODOT or for other agencies here in this region. How often do you use it? Most people only use it on special occasions, birthdays, Valentine's Day, and stuff like that. I was sort of trying to be funny when I wrote the question only on special occasions, but I think it's very true that there are going to be times when people will need data from this system. There are 0% of the people use it on a daily basis. We'd like to increase that a little bit so that and 3% never use it. That was really discouraging. But there are people, they could be former students or people who left transportation or something after taking a class from me. How easy is Portal to use? Most people thought that it was either neutral or pretty easy. 23% said it was difficult, so those are and we know who those people are. So what we want to do is use this to target some training or some further, to find out, well, if we describe to you more in detail or walked you through different steps, would you use it more? And so that's really of interest to us. Of all the different tabs in the system, which do you use? This is just sort of showing that the time series and the congestion plots were pretty popular, as well as the incident reports. 21% of the people said they had some examples they would share with us about how they've used it, and I'll show you a couple of those in a minute. We were asking people what areas they would like us to focus on for future extensions, so we had them rate these 7 possible extensions on a scale of 1 to 5. The arterial performance that Matt and Michael talked about earlier, and John, it was the most popular. The variable message sign one was pretty popular. We've got some other future extensions of the project that we'll be working on in the future, we hope. 10% asked for a demo, so that was also very useful for us. So we're setting up some meetings and conversations with people who want to learn more about Portal. And just like this seminar is an example. So there are a couple success stories based on this survey. I think I'm going to skip some of this. We're using the Portal system to evaluate the ramp metering system here in Portland. Max Kaufman, who I think is here, has was working as an intern at PDOT this summer and also has been working in Commissioner Adams' office. And basically, Max used Portal to prepare this incident autopsy, as he called it. And I think the story was Commissioner Adams saw an incident on the freeway or got stuck in the queue upstream of an incident. And this just shows how Max was able to go into the system. I guess the next day you could have gone in and pulled the data out and said, well, here's the congestion that resulted from the incident. From ODOT, we could get a whole trace of all the details of what happened at the incident. The variable message sign was up about 12 minutes. It took about 12 minutes after the crash occurred for the VMS message to go up. So the crash happened at 8:15. By 10 o'clock, traffic was moving again. And then this is a volume plot showing when the crash occurred, when the tow truck arrived, when the lanes were cleared, but took a while after the vehicles were removed for traffic to get moving again. But I think this kind of an analysis of one particular incident wouldn't have been possible if we didn't have these tools available. So this is one example. If there's something that occurs, ODOT and the City of Portland can go in and do a debrief on a major incident, and they have the data right at their fingertips to be able to determine what happened and how to do better the next time. And I think this has resulted in some new focus at the City of Portland and at ODOT on speeding incident response, and there's a new task force that Commissioner Adams has pulled together in order to improve incident response capabilities. So hopefully we had a small influence on the success of that project. John Mackler over at Metro has provided me with a couple examples. This is, of course, Metro is developing the update to the regional transportation plan, and this is an example of some seasonal analysis that they have been doing. Basically, since we started the project, they can look at seasonal average speeds by freeway segment over time and see how those have been changing. They can also do cross-section studies, so this is just an example of something that John has put together. Highway 26, many of you know, was widened over the last few years, so you can focus on a specific segment and look at perhaps speed showing before the widening and after, and then you can also analyze the impact on the traffic volumes that were measured at a particular location over time. And again, an analysis like this might take 5 minutes, at least that's what John told me. If you didn't have access to a system like Portal, it could take a month because you'd have to request somebody to go out and count the traffic, and you would hope that you had data from the past. This is the idea here is that this kind of thing can almost become automated, taking advantage of the data that's in our database. John also did a cross-section analysis from 8 different locations around the region, and just as an example, categorized the measured speed, and this is for 2005 on mid-weekdays. You know, you can look at a whole year's worth of data just in a few minutes. So he took a look at speed and kind of put things at 55 and above in the green area. Something might be wrong with that detector there, but or we just need some more enforcement out there. In the yellow area, here's an area where maybe you want to look at some possible congestion, and then in the red area, this particular speed plot comes from northbound I-5, where there is a small project going on that some of you may have heard about, the Columbia River Crossing. There are also several freeways in Portland that essentially form a T, which he called a geographic bottleneck. So you have 26 that kind of comes into downtown on the west, and 84 kind of tees into I-5, and those are kind of classic bottleneck problems where you're going to have lower speeds. But the idea was there, again, in order to look at a real average speed over a whole year prior to the presence of Portal would take a lot of work. So John and his colleagues at Metro and the City of Portland and ODOT are working hard to strengthen the planning and operations connection, and at least he tells me that Portal is helping him do that. And this is a document that's available on Metro's website that they recently produced in trying to educate people about some of the aspects of intelligent transportation systems. They produced this document called Metropolitan Mobility the Smart Way that talks about some projects, including the Portal project, and that's available on Metro's website. Jim Mayer at the Oregonian and some other reporters at some other local newspapers have been using Portal data. This is an example of how the Oregonian has used the Portal data on the right-hand side to, I think, raise some level of understanding about how the transportation system is operating for the public, which I think is great. And this was from the, what was this from? Portland Tribune, another example of how we give them a login username and they can produce the data and produce some plots from our data source. Getting ready to wrap up here, and maybe we'll take some questions. I mentioned some of the expansions already. ODOT has some historic data going back to 1995. They have some 15-minute data that we'd like to incorporate pre-2004. We've got a chunk of TriMet data. We're working with them to bring that into the database on a continuous basis. Washington DOT data, like I said, any day we should start receiving, and it'll just show up. So if you log in, you'll see the speeds on our maps from the Washington side. ODOT has a number of way in motion stations around the state, and we've talked about adding that to our system. And we're just interested in adding other useful tools, so if any of you have ideas, you can give us some feedback. And how do you do that? Well, first you come to our website and request an account, and the last slide, I think, has the web address on it. You just fill out a quick form. Once you become a user and you have some experience, we're anxious to receive your comments, and we have a comment form that you can submit as well. And I guess I was right. The web address, portal.its.pdx.edu, is the location. We have lots of folks to acknowledge the funding for the project has initially come from the National Science Foundation. ODOT and the FHWA have also supported the project, and we have some new funds from FHWA for the next few years to expand and improve the system. The Regional Transport ITS Coordinating Committee has been supported from the very beginning. City of Portland, TriMet, and ETIC have also provided some funding. And I list a number of team members, former team members, and current team members who I want to thank for all their work. And also I want to acknowledge the folks down in California with PEMS, Carl Petty, Praveen Varaya, and Alex Gabardonis, essentially have been great partners inspiring us to develop Portal. So thank you for your attention, and I'd be glad to deflect any questions you have to the team members who are here with us. So please use the microphone.
How do you estimate occupancy?
Well, occupancy is something that's, I should have mentioned before. Occupancy is directly measured, and it's the time that the loop detector is actually covered by a vehicle. So vehicle occupancy in terms of number of people in the vehicle, we don't measure, and there is no way to measure it except by looking. I would expect in the future some vehicles know whether there's a person in the seat, so they have seat sensors for airbags and things like that. So perhaps in the future we could get vehicle occupancy from the vehicles, but for now you've basically got to stand on a bridge and count. Aaron.
Matt talked a bit about the effort to make the behavior of buses look more like the behavior of cars, and I think he mentioned removing the dwell time. Mm-hmm. Is there a way to account for the acceleration, the deceleration when they're getting to a stop, when they're leaving?
Do you want to use the microphone?
Sure. So the question is there a way to account for when the bus is accelerating and decelerating?
Right. Because theoretically the car would not be going through
right.
that process.
And I mean, it's not explicitly, it's not a database field, and I'm not exactly sure how you would create that. I mean, one thing in speaking with TriMet, one interesting thing about the project is that the database right now is structured in a way that's useful for them for evaluating the transit performance, which has been really useful for them. But there are other fields that could be easily added. But I've seen studies in which they use bus data to create algorithms for estimating travel time, and they include that, or they try to include the deceleration and acceleration, but I think ultimately they found it wasn't telling them. There was simpler things for them to do. So, but there's no real easy way to do that with the data as it stands.
And we had a previous project that found that the maximum speed between stops was a pretty good indicator of actual speeds, because we sent out some probe vehicles that were out there with the buses. The maximum speed between stops over-predicts the actual speed a little bit, and we found on Powell that it did so by about 5%. So ultimately, we plan to expand, the project to do some testing to see whether that 5% number holds on other arterials, and also depending on bus stop spacing, if the stops are very closely spaced, the maximum speed might be pretty good. Other questions?
As far as other municipalities doing similar type of projects, worldwide, I know in Europe they're doing a lot of similar type of thing. Are there certain ones that were used as a model, and then also are there other ones, or the same ones, that are looking to you guys as a model for how to solve some of these issues?
Well, within the United States, there are probably 5 or 6 ITS data archives that are sort of open and public and visible like ours. I mentioned PEMS in California. Maryland has one. Washington has one that they're trying to develop. Virginia, Maryland. So we're plugged in a way to the other entities doing this. I think people are looking to us to see what we're doing here. Ours is a little different than some. I mean, on one hand, we benefit from the fact that the Portland region is of a relatively manageable size. In California, PEMS is a statewide system with 25,000 detectors. Here we've got 500 detectors on the freeways, which is a good number, and 25,000 is just so big, and the things that they can do on a statewide basis are just different. Also, I think the data sharing attitude here and the idea that the agencies, we have Don Crown over here from ODOT, he's interested in helping improve the system. So we have true partners who are anxious to make this thing work. So that's a little bit different. Though we do look around at the rest of the world in terms of the arterial performance, this sort of vision to bring the arterial performance online is something that you can look at the London system, Paris, Los Angeles. They have arterial performance websites where you can look at the color of the road in real time, and so we're using that as inspiration as well.
I have a question. So all the data is freely available. That's one thing to make it quite clear. Have you had any problems getting any sources of data with them not wanting it to be redistributed?
Not really. Not really. For the most part, most of this data is not too sensitive. So for the most part, the data sharing mentality is pretty strong. Other questions? Online viewer?
Yeah, so we have a note, Matt. Your mom says good luck on finals. Do you think the portal will be useful when the 205 light rail line opens for evaluating its effect on the freeway's performance?
Sure, yeah. And I mean, we'll be able to look at how the freeway has been performing since 2004. So before and after. One of the problems with construction, however, and we found this on Highway 26 and on Highway 217 recently, is that the detectors we use are actually cut into the pavement. So if you are paving or if you move lanes around during construction projects, which happens, then we actually lose the data. So because we're relying on inductive loop detectors, if you do have a construction project, essentially you can just assume that the data will stop coming in during that time. With 205, they've preserved the right-of-way when they built the freeway, so my guess is that there won't be too much of an impact during light rail construction on the freeway lanes themselves. But we had the problem on 26 where for a long time we didn't get any data. 217 last fall, they repaved, and we lost a lot of data from that. Aaron, did you have another?
I was just curious, on the composite monthly plot that you showed early on, there was a pretty pronounced spike in the 95th percentile right after the morning peak that wasn't reflected in the mean speed. Do you have any idea what's behind that?
On that one, I'm not sure. I mean, sometimes if you have an incident or maybe some sort of, I don't know.
I just have a question about some of the TriMet data.
Sure.
One, I was curious, how is the data collected when the doors open and close? And then also, are the number of passengers that go on and off, is that collected, used?
Yeah, maybe I can give a quick answer and then Matt can expand. But every bus, we didn't get into too many of the details of that, so it's a good question. But every bus has a small computer on it, and it has a little card that the operators insert in the morning. Contains the schedule, and then every time the bus stops, a row of data is written to that card. And I mean, the door is computerized, so when the door opens, that signal is sent to the computer, and then there are automatic passenger counters that use little infrared beams. So next time you get on the bus, there's a little panel about this big with 2 holes in it, and one on the other side. And so when you break that beam in the right order, it counts you as a passenger coming on. And one of our colleagues, Jim Strathman, worked with TriMet a few years ago on a project to validate the accuracy of those counts. And so TriMet uses those automatic counts to do their official FTA reporting. Most other transit agencies hire people with clipboards, essentially, to go out and count on the vehicles. But those are 99% accurate automatic passenger counters. Then all that data is downloaded at the end of the day. So some of the stuff we were showing you is using that end-of-day data, and it's a little different if you want to do something in real time. Good question.
When you run an analysis in Portal, you get a zip folder of 20-second data. Are the Portal graphs actually based upon the 20-second data? Or
The plots that we showed are using 5-minute averages, so the system is set up to every night essentially produce 1 hour, 15-minute, and 5-minute tables to allow you to quickly graph things. There are some graphs that you can do using the 20-second data. They just take a little longer to process. And then, of course, like you said, as you've had some experience for my class, you can download the 20-second raw data in a zipped file and do your own processing offline. Any other questions? Well, thank you very much for your attention. And I believe the first seminar of spring term is not in a dissimilar theme. Fred Liang from the city of Bellevue, Washington, will be talking about their arterial performance project in Bellevue. So we'll look forward to seeing you then. And I think any students, your papers are due on Tuesday to your instructor, either Professor Dill or Professor Monsieur, by 5 p.m. on Tuesday, and I believe they accept email versions of their diaries. Jennifer likes the paper version. So thanks for your attention, and good luck on your finals.